Welcome. The intellectual history of the 20th century was defined by finding limits, the speed of light, the uncertainty principle, and finally, the boundaries of what can be computed. Today, we move beyond simple solvability to the rigorous study of intractability. We will explore complexity theory, formally defining the classes P and NP, and analyzing the Millennium Prize problem that asks if creativity can be automated.
Just because a problem has a solution doesn't mean we can find it before the universe ends. While Alan Turing defined what is computable, complexity theory defines what is feasible. We are measuring the cost of computation, specifically how the required time and memory scale as the input grows. Think of it as the difference between knowing a chess game can be won and actually having the time to calculate the winning move.
The field rests on two pillars. On the left, class P, problems we can solve efficiently. On the right, class NP, problems defined by efficient verification. It is a common misconception that NP only contains hard problems. In reality, NP contains all of P. Easy problems are obviously verifiable, but it also includes problems where finding the answer is difficult, yet checking a provided answer is trivial, like a jigsaw puzzle symbol, but instantly recognizable when finished.
To define these classes mathematically, we need a standard model, the Deterministic Turing Machine, or DTM. It uses a finite set of rules, a transition function, to manipulate symbols on a tape one step at a time. Crucially, it is deterministic. Given a current state and a symbol, there is exactly one next move. When we say an algorithm takes polynomial time, we mean a DTM can solve it in a number of steps bounded by n to the power of k.
Now, imagine a machine that isn't limited to one choice. The Nondeterministic Turing Machine, or NTM, can branch into parallel universes at every step. If it faces a choice, it takes all paths simultaneously. It accepts an input if just one of those timeline branches finds a solution. This represents a lucky guess. This theoretical machine is the foundation for the class NP. It solves problems by guessing the answer and verifying it efficiently.
Let's formalize class P. Mathematically, it is the union of all deterministic time classes bounded by a polynomial. We rely on the Cobham-Edmonds thesis, which asserts that P is the mathematical synonym for feasible. Whether you use a supercomputer or a laptop, if a problem is in P, it is robustly solvable. Examples include finding the shortest path on a map, or checking if a document contains a specific word.
Conversely, class NP is defined by verification. A problem is an NP if provided a certificate or witness, call it C, a deterministic verifier can confirm the answer in polynomial time. For example, in the Hamiltonian path problem, finding a path visiting every city once is hard. But if I hand you the list of cities in order, the certificate, you can verify it works in seconds. NP captures the asymmetry between creating a solution and appreciating it. How do we prove a new problem is hard? We use reductions. We take a problem we know is NP complete, problem A, and transform it into our new target, problem B. If we could solve B efficiently, the transformation allows us to solve A efficiently. Since A represents the hardest problems in NP, B must be at least as hard. This effectively transfers the property of NP completeness from the known problem to the unknown one.
At the peak of difficulty lies NP completeness. These are the universal problems of NP. A problem is NP complete if it is in NP, and every other problem in NP can be reduced to it. The Cook-Levin theorem proved that Boolean satisfiability, or SAT, was the first such problem. If you find an efficient algorithm for SAT, you have instantly solved every hard problem in class NP, from protein folding to cryptography.
Following Cook, Richard Karp demonstrated that this wasn't a fluke. He showed that 21 standard problems, including the traveling salesman problem and graph coloring, were also NP complete. He did this by chaining reductions, reducing SAT to 3SAT, and 3SAT to clique, and so on. This revealed that intractability is widespread across combinatorics, logistics, and network design.
This brings us to the most profound open question in computer science, the P versus NP problem. Simply put, is P equal to NP? Can every problem whose solution can be quickly verified also be quickly solved?
The stakes are incredibly high. If P equals NP, modern cryptography collapses immediately, as private keys could be derived efficiently from public data. Conversely, the consensus view, that P does not equal NP, implies a universe with a complexity gradient. Under this assumption, Ladner's theorem proves that intermediate problems must exist, problems harder than P, but not NP complete. Integer factorization is widely conjectured to be one of these intermediate problems.
The landscape extends beyond just P and NP. We have co-NP, where we verify that no solution exists. We have P space, containing problems that can be solved with limited memory but massive time. P space includes optimal strategies for games like generalized geography. Generalized chess resides in exp time, a class containing P space. While we suspect exp time is strictly larger, rigorously proving this separation remains a major open challenge.
Finally, we must address the quantum elephant in the room. BQP is the class of problems solvable by quantum computers. While algorithms like Shor's algorithm can break specific encryption methods by factoring integers efficiently, most experts believe quantum computers cannot solve NP-complete problems. They shift the boundary of tractability, but they do not erase it. The event horizon remains.
In conclusion, the classification of P, NP, and NP-complete is not just taxonomy, it is the map of our intellectual limits. Intractability appears to be a law of nature, akin to the conservation of energy. Until a proof resolves the P versus NP question, we proceed with the assumption that some problems are inherently hard, guiding us toward approximation and heuristic solutions in the face of the computational event horizon.